All right, so what I did was I took my notes, my proficiency scale thing that I gave you, and I folded it in half, and this is the inside, and so we're going to take some quick notes on the left side and right side. So here we go. I'm going to hide that button. There we go. So everything this week is about Newton's second law, so make sure you write this down. Newton's second law is just a mathematical equation that says F equals ma. So let's just define each one of these things. So definitions. So definitions of these. F is just force. M is mass. And A is acceleration. Force is simply just a push or a pull. So if you say have a box that you need to be pushing on, you're forcing it a direction, that is a force. So force is a push or pull. Mass. Mass is the amount of stuff in an object. So like metals have a lot more stuff than say things like plastics. Metals are way heavier because they have more mass. They have more stuff within their objects. So the words you're going to be seeing this week are matter, which is just another fancy word for stuff. And the last one is acceleration, which is pretty much just to speed up. So if you started running in a direction and you sped up as you ran, you would be accelerating. But in a science class, it doesn't just mean speed up, but it also means to slow down and change direction. This is only in a science class. If you get pulled over with a speeding ticket and they said you accelerated too quickly, they're talking about speeding up. But truly, the true definition of acceleration also means to slow down or change direction. So there are units for each one of these. Units. And you're going to need to know these units, or this week is going to be kind of hard. So units for force is the Newton, named after Sir Isaac Newton, and Newton's second law. Oops, it's just S, which is represented by the letter N, and it's capital N, and the capitalization does matter. So you'll be seeing things like 5 N, or 5 newtons. For mass, it's kilograms. Kilograms. That's going to be a lowercase k and a lowercase g. And so you'll be seeing things like 1 kilogram, which, by the way, 1 kilogram is about weight of a water bottle, a pretty big water bottle. And the last one is meters per second. Meters per second per second. By the way, the word per means to divide by, so you'll be seeing things like 10 meters per second, or 10 meters per second with a little 2. That's called a superscript 2. This is hard to type on a computer, so sometimes you'll be seeing this. They mean the same exact thing. It's just meters divided by seconds, divided by seconds, divided by seconds twice. All right. This week, you will be responsible for doing some of these math problems, and honestly, there's a really quick cheat method for doing these math problems. And it's this triangle right here, where we write force, mass, and acceleration. I'll put a multiply sign in between here, and then I'll also put a divide sign here, and I'll also put a divide sign here. And so as long as you know 2 of these things, you should always be able to solve for another one. That is simply algebra. To speed up is algebra, we use this triangle. So say we're solving for force. So say we don't know the force of an object in newtons, but we know the mass. And let's say the mass is 5 kilograms. and we know the acceleration. Let's say that's 2 meters per second squared. The way to solve for this is you just cover up what you're trying to solve for. So if I cover this up, I know I'm going to be multiplying mass times acceleration. So let's just do that. So it's mass, 5 kilograms, times acceleration, 2 meters per second squared, results in 10 newtons. And there's my answer. Now, units are important. You have to have units in this class. Think of this part of science as a small math class with units. Okay, so you got to have the units. So we solve for force, but there's two other problems that we could possibly do. What if we don't know acceleration? We do know force. Let's say force is 10 newtons. And say mass, we know it's 5 kilograms. But we don't know the acceleration. How fast is it speeding up or slowing down or changing directions? Well, all we do is we cover up the A, and it's going to be force divided by mass. So 10 newtons divided by 5 kilograms results in 2 meters per second squared. We're just going to ignore the pledge going on in the background. Let's solve for the other one here. What if we don't know mass? So we know force. Let's say that's 10 newtons, but we don't know mass. Mass is, we don't know, kilograms. And acceleration is 2 meters per second squared. We just cover up this one, and we know it's going to be force divided by acceleration. So we take force, 10 newtons, divided by acceleration, meters per second squared, and that's going to give me 5 kilograms. There's our answer. Voila. So coming to our other side, let's talk about how Newton actually wrote this equation. He didn't actually write it force equals mass times acceleration because he wasn't trying to explain force. He was actually trying to explain acceleration, and he actually wrote it this way. It's the same exact equation, we just moved it around a little bit. And that'll help us explain a couple of different things whenever we're looking at data. So we'll make just a little bit of data real quick. We'll have acceleration, we'll have force, and we'll have mass. And we'll just put it on a table here. So let's say we keep the mass exactly the same, 5, 5, and 5. But we increase the force, 10, 20, 30. So say we have a shopping cart, it weighs 5 kilograms, and we give it a little bit of force, we give it some more force, and we give it a ton of force. What's going to happen to the acceleration? Well, doing this equation, force divided by mass, this would give me 2. 20 divided by 5 would give me 4. 30 divided by 5 would give me 6. And so the acceleration is going to speed up. And so on a graph, this would look like this. Doot, 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 doot. And we'll say this side is acceleration, and we'll say this side is force. And force, we did 10, 20, 30. And acceleration, let's just go with their numbers. We have 2, 4, 6. What happens is these numbers, or this line, is going to be going up. Let's look at the other side of this. In fact, let's just split this down the middle here. So that's if we change force, but what happens if we change mass? Let's go to this side. Acceleration, force, mass. And acceleration, let's just keep the force the same this time. So we'll keep it 10, 10, and 10, but we're going to increase the mass. Let's go 5, 10, 15. So as an object gets bigger, but we keep the same amount of force, what's going to happen? Is the object going to speed up or slow down? Think about that shopping cart. We're going to keep pushing it with the same amount, but we're going to keep adding stuff into the shopping cart. And we're pushing it with the same amount of force. Something tells me it's probably going to slow down. So let's just do this real quick. 10 divided by 5 is 2. 10 divided by 10 is 1. And 10 divided by 15, I believe it's like 0.666 repeating. So it does get smaller. And so if we put this on a graph, the graph's going to look something like this. So that's 5, 10, 15 for mass, and acceleration, let's say, is 1 and 2. So as the mass increased, the acceleration is actually going to decrease. So we have a graph that goes up, and we have a graph that goes down. These types of graphs have names. Before I talk about the name, I'm going to go ahead and push this a little bit harder. We have acceleration, if we equals force over mass. If we keep mass exactly the same, but we increase force, the acceleration will also increase. But if we have acceleration equals force divided by mass, and we increase the mass but leave force exactly the same, the acceleration will decrease. Since both of these are going up, and this is going up, this is known as a direct relationship. That's a test question right there. And say this is going down, and as one goes up, the other one goes down. That's known as an inverse relationship. Inverse relationship. We see these patterns all the time in data. As one goes up, another one goes down, or as one goes up, the other one goes up. Direct relationship, one goes up, one goes up. Inverse, one goes up, the other one goes down. We're going to be seeing that a lot this year, so this is actually a pretty good place to start talking about it. There's your notes. Best of luck.